All right, in this video, we're going to be talking about section 3.3, the properties of logarithms. We're going to try to do this pretty quick. To start, let's go ahead and focus on this warm-up. Why don't you go ahead and pause the video and see if you can piece together the answer to the log base 4 of 8. All right, when looking at log base 4 of 8, the correct way to handle this would be to first start by probably thinking of it as an exponent. So this is basically saying 4 to what power is equal to 8. Now, if you think about this, there's probably a couple of ways of doing this. We'll do it both like a very algebraic way, and then we'll also do it more of a logical way. So in an algebraic way, we can notice that both 4 and 8 both come from a base of 2 themselves. So in other words, let's go ahead and we'll just make this a little more algebraic. Let's call this x. And so 2 squared is 4. So we have 2 squared to the x power. And 8, of course, is 2 cubed. And so that means, because the power to a power rule means we multiply, so I have 2 to the 2x equals 2 cubed. And so if these two numbers have to be equal, then that means their exponents have to be equal. So then I can just take these two numbers and set them equal to each other and solve, and I get 3/2. All right, so that's a very algebraic way of analyzing this and getting the answer. But for me, that's not how I would generally approach a question like this. What I would do is have the same notice that they both come from a power of 2. And so let me rewrite the problem here. Let me change my pen. 4 to the x equals 8. So the first thing I would do is I would just ask myself a question. What can I do to 4 to get it down to a base of 2? Well, I could raise it to the 1/2 power. So 4 to the 1/2 power is 2. And then if I want to turn that 2 into an 8, then I would just have to raise that to the 3rd power. In other words, I would have 4 to the 3/2 power. So the 2 takes the square root, and then the 3 brings it back up and turns it into 8. So the answer is what power? The answer is 3/2. So log base 4 of 8 equals 3/2. All right, so let's take a look at these properties of exponents. Now, these are ones that we know, or most of them we know. And so if a to the x equals a to the y, that means that x equals y. And hopefully that makes perfect sense. We sort of just used that one a second ago in the warm-up. We know that a to the 0 equals 1. And I know that a to the first is a. And now let's take a look at a to the log base a of x. And I think the easiest way to sort of demonstrate the answer here is to maybe look at it as a quick number example. So let's just say that we're going to answer the question 2 to the log base 2 of 8. Okay, so first, let's figure out the answer to that question right there. Log base 2 of 8 is saying 2 to what power is 8? And so the answer to that question is 3. So this becomes 2 to the 3rd power, which is 8. Okay, so let's think about what's happening here. This question is asking us to find a power. And what power is it looking for? 2 to what power is 8? And then what are we doing once we get that answer? Well, we're raising 2 to that power, right? And so we just said the answer is 3, so 2 cubed is 8. That will be the same regardless of what I do, right? So let's see if that works out the same for some that doesn't work. Let's say 3 log base 3 of 8. Now, I don't know what power to raise 3 by to get 8, but there is an answer, whatever it is. What are we doing with that answer? So we get that number, and then we're raising 3 to that number. Well, that is the number we just said is what we raised 3 to get 8. So we get back to the number itself. So long story short, what this answer is x. A to the log base a of x simply gives us x. It simply returns the value inside of your logarithm. Okay, let's keep rolling. A to the x plus a to the y, that comes from taking a to the x times a to the y, right? Because we're using that rule sort of in reverse. We know that when we're multiplying numbers with the same base, we add the exponents. So that becomes a to the x plus y. So ax minus y becomes a to the x, a to the x divided by a to the y. And if we're dividing numbers with the same base, we subtract their exponents and you get x minus y. And then we know that this one is a to the x to the y power. So if we have exponents being multiplied together, then we could look at it as power to a power. All right, so each of these exponent rules has a related logarithm rule. And so let's take a look at some logarithm properties here. So if I have log base a of x, and that equals log base a of y, then just like over with the exponents, if I'm taking log base a of log base a of two different numbers and they're equal, then the only way that would be possible if the two numbers themselves were equal. All right, the related one to a to the 0 would be log base a of 1 equals 0. And we know that from many different ways. Number one, just rearranging it back into exponent form. But also our graph of log base a, we know that the x-intercept is 1. So when I insert 1 into the equation, I get an output of 0. And we know that if we take log base a of a, that's going to equal 1. All right. And then we get this one. The equivalent statement here would be if we took log base a of a to the x. So log base a of a to the x. So let's think about what that's asking. That's asking a to what power equals a to the x, right? A to our unknown power equals what's inside the logarithm. And so hopefully it seems quite obvious that our missing number would have to, in fact, be x. If we have a to the power equals a to the power, then the two powers have to be the same. So these two together are basically our inverse operations. Taking log base a of an exponent is going to get us down to the exponent. All right. And then we have two rules here that are related, and I'm just going to give them to you. If we have a statement of log base a of x plus log base a of y, the rule tells us, and hopefully you remember from last year, that you get log base a of x times y. Don't need the parentheses there because when you're taking the logarithm, you're doing it, it's understood that these two factors would both be together. You would need to do parentheses if you had two terms. But sometimes just putting the parentheses, even if they're not needed, helps it be more readable. All right, and then we have a rule that says log base a of x minus log base a of y equals log base a of x divided by y. And finally, we have one that says log base a of x, and then that x is being raised to the power. There's a property that tells us that we can take that power, bring it down, and multiply it by log base a of x. So essentially this power moved down and became a factor down here. So these three properties are our major new rules that we're going to talk about in this section. These are kind of referred to as our expanding or condensing rules, because we can take two separate logarithms and condense them into one, or we can take one and expand them into multiple. All right, so I've decided not to go through the proof of this, but let's just kind of look at a comparison and see that it's not sort of outlandish to think that these would do this. So for example, back in our exponents, we had a multiplication question, and that multiplication question turned into us doing some addition. So here we are, we have a multiplication inside of a logarithm, and that turned into addition. Here we had division that turns into subtraction. Here we have division that turns into subtraction. And then this one, maybe a little bit, it doesn't make direct connection here, but we had a power turned into multiplication. And here we had a power and it turned into multiplication. All right, so by no means is that a proof of anything, but it is sort of a, hey, it's not outlandish that these would be connected. Okay, let's now look at some illustrations of these and see that they do in fact work. So in order to do this, let's answer these two questions, log base 2 of 4 plus log base 2 of 2, and let's answer them two different ways. The first way, let's just answer it as it stands. So log base 2 of 4 is saying 2 to what power is 4? So the answer to that question, let me give myself a little room here. The answer to that question is 2. Plus log base 2 of 2 is 1. And so this has an answer of 3. But if we use our condensing rules, the rule for addition tells us that I can rewrite them into one logarithm with the same base, and then I would multiply those two together, which of course is log base 2 of 8. And 2 to what power is 8? The answer is 3. So still not proof of this, but an indication that it does in fact work. Let's try another one. Log of 100 is saying base 10, so 10 to what power is 100? That's 2. Plus log of 1 over 100. 1 over 100, log of 1 over 100 is going to be taking a base 10 and squaring it, so the answer is 2, but then we have to flip it over, so it becomes a negative 2. So it looks like the answer to this question should be 0. And let's use our condensing rule again, which says take these and multiply them together, which of course gives us log of 1. And log of 1, 10 to what power is 1? The answer would be 0. All right, let's look at an illustration of the subtraction to division one. All right, so once again, let's answer this separately. 3 to the third is 27, and 3 squared is 9, so we get an answer of 1. Our condensing rules say that they have the same base, so I can bring them together as a division question. So 27 divided by 9. Make sure you don't write log divided by log, but it's log of two numbers being divided. That's a pretty common error, is to kind of mess that up. All right, we know that 27 divided by 9 is 3. So this is log base 3 of 3, which we know to be 1. And let's do one more. Log of 100 is 2. Log, we've done this one before, so minus 1 over 100 is going to be negative 2. So I have 2 minus negative 2, so that should be 4. Let's condense these, which says I take 100, divide it by 1 over 100, which gives us log multiplied by the reciprocal of 1,0,0,0,0, so 10,000. And so 10 to what power is 10,000? It would be 10 to the fourth, because 4 zeros would be 10,000. So it still works. And let's illustrate our third one. All right. So this one, let's answer separately. So let's answer this part of the question. Log base 2 of 8 is 3. And so this problem says 2 times 3, so the answer should be 6. All right. The condensing rule says that I can take this power, or that number, and bring it up and make it a power of 8. So I have log base 2 of 8 squared, which of course is log base 2 of 64. And 2 to the 6th power is 64, so the answer is 6. All right, one more. The cube root, I'm sorry, not the cube root, log base 3 of 1 over 81. What number raised to the 3rd power is 81? Ooh, I think I made an error on this one. I think I probably meant to say 4th power, so let's just change it. All right, let's see what this does. No, that's not what I meant to do. Hold on, I'm being stupid. All right, I'm back. Ignore that. 3 to what power is 81? The answer would be 4, but I've got it as 1 over 81. And so that means the answer would be negative 4. 3 to the negative 4th power would be 1 over 81. 3 to the 4th is 81. The negative flips it over. Sorry about that. My brain shut down for a minute and had to reboot. Half of negative 4 is negative 2. And so that answer should be negative 2. Our condensing rule says we can raise this up and make it a power. And what does it mean to take a half root power? We get the square root. So the square root of 1 over 81 is going to be 1/9. This log base 3. So 3 to what power is 1/9? And the answer is negative 2. Okay, so we've illustrated they work. Now let's use them. All right, so for these first couple, we're going to use our rules to fully expand our logarithms. So please pause the video and give these a try. You'll notice on part B, I have a natural log, but that's still just a log, so all the rules apply. Okay, so in analyzing A, I see we're doing log base 4 of 3 separate factors, 5 times an x cubed times a y. So I'm going to do this. I mean, if I was doing it for myself, I'd do it in one step, but I'm going to illustrate it a little slower for you guys. So I know that I can make this log base 5 plus log base 4 of 5, log base 4 of x cubed, and log base 4 of y. So I can separate them all out into different terms. And then I look around and there's really not much else to do except I can use rule 3, my exponent rule, and I can turn this into log base 4 of 5 plus 3 log base 4 of x plus log base 4 of y. And that would be fully condensed because I can't apply any of those rules. There's no more rules to apply. All right, the key here on this backup to A real quick before we move on is don't get caught up with this 3 and think you can bring that out in front at the beginning because this 3 is only applied to the x. So I can only break it out and bring it to the front once I've isolated just down to a log of the x. Okay, in this problem, it looks to me like we have a division. So I'm going to do this in 2 stages, I think. The natural log of the numerator minus the natural log of the denominator. All right. Next, notice that this is actually, we could just rewrite this if we wanted to. We can raise it to the 1/2 power because that's what a square root is. So I can bring that 1/2 down in front. And then this is as far as it goes because don't get confused. This is a 3x minus 5 inside of the logarithm. we have no rule that tells us that we can separate terms into anything. We can bring terms together, two separate logarithms as terms into one, but we have no rule that says if you have terms inside of a logarithm, we can do anything with that. So we are, in fact, done right here. Okay, so just to make sure you understand what I'm saying, we don't have a rule about this situation. Like, we don't know anything. It's certainly not this, right? Because if it was this, we know by the rule that if you have natural log of A plus natural log of B, then that would be the natural log of A times B, not A plus B. So, long story short, we have no rule that helps us deal with terms. All right, now let's go the opposite direction. Let's practice doing some condensing. So now let's bring them together. So I'm looking at part A here. I'm seeing two very distinct terms. So before I worry about bringing these two terms together, I'm going to inspect each one. So this term, I have a power out front. So the rule 3 tells me I can rewrite that to be log base 10. You know what? Let's just call that log of x to the 1/2 power, which we might as well call that what it is. That's the square root of x. Plus, that 3 can use the same rule, and it can be x plus 1, the whole quantity cubed. Now it's a plus, so that tells me I can bring them together into, there's going to be a couple parentheses here, so I'm going to use a bracket here. The square root of x times x plus 1 cubed. And unless I want to get super tricky with something, that's about as far as I can go. Okay. Part B is going to be pretty similar. I have a 2 only attached to this term, so it's going to be, I deal with that power first. So that turns into natural log of x plus 2, the quantity, squared. And then I'm subtracting two different logarithms, so then I can combine them together into one logarithm. And I get that statement right there. All right. And let's look at part C. Part C, we have a 1/3. I could, if I wanted to, I could distribute that first, and then I'd have 1/3 on each of the log statements. But I think it's going to make more sense just to simplify the inside and then deal with the outside. So I think we're going to have 1/3, and then inside I've got log base 2, and these are going to come together as x times x minus 4, which I could multiply and make x squared minus 4x if I want to. And then I can use my power rule and make this log base 2 of x times x minus 4 all to the 1/3 power, right? So I could either do this, but that looks ugly and messy. So instead, I'm going to treat it as what it really is, which is the cube root. And if you want to multiply the x together, that's fine. It doesn't hurt anything, but that's as far as we can go. All right, let's do a couple more problems with expanding and condensing. All right, let's use our properties of logarithms to evaluate each expression. All right, log base 4 of 2. I could make some progress with that on its own. 4 to what power is 2? That would be 1/2. 4 to what power is 32? I could bring the 4 down to a 2 by raising it to the 1/2 power, and then I would have to turn that into 32 by raising it to the 5th power. So in other words, I'm saying the square root of 4 gets me to a 2, and then raising that to the 5th power makes it 32. So in other words, this is going to be plus 5/2. 1/2 plus 5/2 is 6/2, so the answer should be 3. Well, I didn't really use any properties of logarithms, so let's see if this would have been a little less cumbersome if I had just used my properties first. So knowing the answer is 3, let's try that one again. My rule says I can bring these together into log base 4 of 2 times 32, which is 64. Now, 4 to what power is 64? 4 cubed is 64, so the answer is 3. So I think, unless the individual logarithm is so simple to answer, I'd probably go ahead and treat them as something that needs to be condensed. So let's condense these. Log base 2 of 80 divided by 5. And 80 divided by 5, I'm pretty sure, is 16. And 2 to what power is 16? That would be 2 to the 4th is 16. All right. Same thing on this one. I think we might have better luck answering the question after it's been condensed. All right. 8 to the negative 1/3. That is telling us to take the cube root of 8, which is 2, and then flip it over. So this is going to be 1/2. So log base 4 of 1/2. So to turn a 4 into a half, to turn a 4 into a 2, we had to take the square root of it. The square root of 4 is 2. I need to flip it over, so let's make it a half. So 4 to the negative 1/2 would make it 1/4, and then the square root of that would be 1/2, which is what we got. All right, let's keep rolling. Use the properties of logs to expand. So we're just going to practice expanding a few more. So this becomes log base 2 of 8 plus log base 2 of x. And while we're here, log base 2 of 8, we know that one. That's 3. So we might as well go ahead and just turn that into a nice, simple 3 plus log base 2 of x. All right, this one, we've got log base 6 of x cubed plus log base 6 of y to the 6th. And then the powers can come down. Bring the 6 down. And there we go. All right. And on this one, let's be careful. That 3 is saying we have the cube root of c. So let's go ahead and do this over here. Natural log of the cube root of c minus the natural log of ab. I can bring this down front as 1/3. So I'm going to have natural log of c. I'm going to have 1/3 times that. Minus, and now I got to be a little careful here. The a plus times b is going to turn into the natural log of a plus the natural log of b. And I just made a very common error. See if you can spot it. That common error is the fact that we're subtracting this one thing, but this one thing suddenly turned into two things. So the way we have currently written it is I'm subtracting this one, but I'm adding this one. So I need to do one of two things. I need to stick parentheses on that, and then I need to distribute. And let's think about what this would look like putting it back together. Okay. So the way I look at this is obviously we've got to, turn this part back into the cube root. But then it says minus a. And so I know that that's going to come together as this. But now it says minus natural log of b. which technically means I would have the cube root of c over a divided by b. But dividing by b is the same as multiplying by 1 over b instead. And so where does that b end up? It ends up in the denominator where it belongs. So the kind of more simple rule of thumb is simply this. If it's a negative in front of the logarithm, then that number inside the logarithm will just end up in the denominator. So a is going to be in the denominator. I'm subtracting this one, so b will be in the denominator too. And so we get our answer of the natural log of a over b. So just be aware when you're condensing this back together, both the a and the b end up in the denominator. All right. So, and then watch your opposite of that when we have to break it up. All right. Last real example. Given that log base a is -3 and log base b is 11 and log base c is -4, evaluate. All right. Well, as it stands, I don't know what log of a is because it's all buried in the middle here. So I hope it's obvious. What we need to do is expand this. So this 100 applies to all of this stuff. So I could do one of two things. I can give each of them the 100, or I could just bring the 100 out front. And then when I expand this, I get 100, and now I'm going to just put everything in parentheses as I break this one up. So log of a minus log of bc squared equals 100 log of a, minus, and then either parentheses or distribute as you go. I'll go ahead and do parentheses right now. Turns into log of b minus log of c squared. And so last bit of cleanup here. I'm going to leave the 100 out one more time. I get log of a. I'm going to distribute that negative minus log of b. I'm going to bring that 2 down on the c squared, but also distribute the negative. So that's going to turn into a plus. Oh, wait, nope. I made a mistake here. This should be a plus already. I already kind of in my head did what I'm about to do. So the negative goes to both, turning into minus. Let's bring the 2 down. Minus 2 log of c. And so I can distribute now the 100 to each of these, or I can leave the 100 out where it is. But now I have log of a, and I know what log of a equals. So the problem now says 100 times log of a is -3 minus log of b is 11 minus 2 times log of c is -4. So I get 100 times what? -14 plus 8. Which is going to be 100 times -6, I think. So I get -600. Okay, so the question may be in your mind of, okay, big deal. So I see us expanding and condensing, but I don't really understand why we need to be able to do that. And I'll tell you that there are a couple of reasons that really are still very, very relevant in solving equations. But one place where this used to be super important was how we used to find logarithms. So back in the day, and I don't even mean that far back, we didn't have super powerful calculators attached to us everywhere we went. In fact, a lot of kids in school didn't have, when I was in high school, it wasn't very common to have a powerful calculator that had a logarithm on it even. And so, and then dating back, this was the 80s, so dating back further than that, it was even, calculators were just not available. And so the question then became, how did one do a logarithm if you didn't have access to a calculator? Well, you could estimate, certainly as we've done in class, but we needed a better tool. And so every textbook used to have what's called a log table. So I've done a little snippet of one here for you. And so what we had to do, if we were going to find the log of something, we had to get pretty creative. Now, number one, we just had to look up the number in a table. And if you think about it, we can't have a detailed table of every single number that exists. And so what we had was a table that, if I'm not mistaken, it basically went, the one I've grabbed here goes a little bit more in detail, but I remember log tables only really going up to 10. I think the one I snipped this from actually went up to maybe 100, maybe it was only to 50. And then what we had to do is come up with ways of finding the log of a number by breaking it down. So, for example, if I had a log table that only went up to 10, then if I wanted to say, like, find log of 200, I couldn't look that up in my table. But what I could do is I could say, you know what? Log of 200 is actually just log of 100 times 2. And I can now break that up and say log of 100 plus log of 2. Well, log of 100, I know the answer to. That's 2 plus, and then I would use my table and look up log of 2. And then I would add that to 2. So you can see these condensing and expanding rules played a huge role in us using and finding logarithms in the past. It's kind of a dying or even dead art form. In fact, I haven't reviewed it recently, so I would struggle to be able to explain most of this to you. But here is like the process of finding a logarithm, especially if you want to find like something very detailed. So if I wanted to find the log of 22.35, so first of all, what's that asking? 10 to what power is 22.35? Well, we know the answer is bigger than 1 because 10 to the first is 10, and smaller than 2 because that would be 100. So we know the answer is going to be very low, something closer to 1 than to 2. But that's about as far as I can go without, guessing and checking further. So the way this would work in our log table, it says, I wrote this out. So if you wanted to find the log, if we're doing log of 22, we would go to row 22. We go to column 3 because our first decimal is 0.3. So if it was 22.9, we would go to row 22 and then go to 9, right? So in our case, we're going to go to row 3, which is 3284. Sorry, the wrong number. Log of 22, 3483. So there's 3483. Then, and again, I honestly I can't remember, like if it's a number bigger than this or less than this, and you go to different rows. I honestly don't remember how this works. Then we'd go over to row 22, column 5, which is a 10, and we would combine them. We'd add them together. That goes into the hundredths place. So the 83 turns into 3493. Then we find the integer portion, which we already know it's going to be 1 because it's, again, like we said, it's between 1 and 2. And so the way you do that is you find the integer portion, the number of digits of your number, and you take away 1. So since we have 2 digits in 22, we take away 1 and get 1. And so then we add 1 in 3493, and we get 1.3493. So I don't expect you to know any of that. I just wanted to give you some context of why the expanding condensing rules used to be like the number one thing you had to learn with logarithms. It's a little less powerful now because our calculators can do all of this for us, but you'll see when we get to solving equations that they'll still come in handy. Okay, we'll go ahead and stop the video here. Check in with me if you have any questions.